All right. Good evening, everybody. We will be starting with the 10th session live problem solving class of the course Essentials of R Software. I'll just start sharing my screen. Okay. So right now, none of the students have joined. So I would anyway start describing what was discussed this week, and then we would take a look at some of the practice questions, and then that should be it. In case people join, then I would also like to go through the solutions of the previous assignment, but we'll get to it at the end. Okay. So these are just some housekeeping notes. All right. So the first thing that was discussed this week was the central limit theorem. So what happens is, let's say we have a lot of independent variables, all following normal distribution. And typically when we are saying normal distribution, we assume that the mean would be some value mu and the standard deviation would be sigma, or the variance is going to be sigma square. That's it. And now, in particular, if all these independent random variables are identically distributed, um, then so now let's say what we are doing is we have many independent and identically distributed random variables. We are not interested in what their original distribution is. They can be discrete, they can be continuous, whatever it is. That distribution would have a mean and it would have a variance, right? Whatever the mean and the variance is, the only condition being is that the variance should be finite. There's just one or two distributions that don't have finite variance, but then we wouldn't go into it. So for all practical purposes, whatever distributions we've taken a look at in the duration of this course, all of those, they can fit into the upcoming theorem. So if we have n independent and identically distributed distributions with a particular mean and a particular variance, then there are two sort of two distributions that can be written from a combination of these original n independent random variables. The first one is about the sum, and the second one is about the mean. So the first one is that when you take a sum of these random variables, then that has a normal distribution. And of course, normal distribution is a continuous distribution. That mean, the mean of that is going to be n mu, and the variance is going to be n times sigma square. So that is a normal distribution. And then we know how to convert a normally distributed random variable into, okay, just a second. Hello, Prakash, can you hear me? Hello, can you just confirm if you can hear me? Okay. I'm assuming you can hear me. So I just started the class and
What you ask?
yeah, you can hear me, right?
Yeah, I can hear you.
Okay, all right. So, okay, fine. It's good that you've joined. I was just on the first slide for today's class. So, all right. So the first thing that was discussed in this week was that, let's say we have n identical and independently distributed random variables. They could be anything. They could be discrete or they could be continuous. The only condition is that they have a particular mean, which we denote as mu, and they have a finite variance, which we denote as sigma square. Right now, we don't need to know what that is, but whatever those values are, for those n random variables, we can define two new random variables. The first one is going to be the sum of the original random variables, and the second one is the average of those original random variables. So the theorem states that whatever your original distribution was, whether discrete or continuous, if you sum all of those up, you would get a normal distribution, and normal distribution is of course continuous. This distribution is going to have a mean n mu and a variance of n sigma square. And we know how to convert a normal distribution into a standard normal distribution, right? So we have that distribution here. denoted as this bit here. And then we can subtract the mean and divide the whole thing with its standard deviation. So in that, it's going to be sigma root n here. Once that happens, this new distribution is going to become a standard normal random variable. Likewise, this theorem can also be applied on the average of x. So if you take the average, then that would have a normal distribution. It's just that now the mean is going to be mu again, and the variance is going to be sigma squared by n. All of these have been discussed. How these things were derived, they have been discussed in one of the previous classes. But once that is there, you can also convert this new normal distribution into a standard normal, right? So you would right. So instead of this thing, you now have this distribution here, right? So this one, what you're doing is you're dividing dividing the numerator and the denominator by n, basically, right? So here it's n, here the n cancel out, and here the root n becomes the denominator. So this is how the central limit theorem is defined. We'll see its application next. Just one thing that needs to be remembered when you're applying the central limit theorem is, so we said that it can be applied to anything, discrete or continuous, right? When you're converting a continuous random variable into a continuous random variable, then it's fine. But when you're approximating a discrete random variable into a continuous random variable, you can just add on these plus halves and minus halves to whatever limits you are interested in. Okay. So that's all. So for any distribution, but when you're approximating it to a normal, so basically questions in this for this topic would be like that you have been given the mean or mean and sigma of some distribution, and you've been given some condition that what is the probability. So for example, in terms of the CDF, that what's the probability of getting a value less than 5, for example. So now instead of the value 5, you may want to use it 5.5 when instead of the original random variable, original distribution, you now want to use normal distribution for that. Okay. So again, this is the exact same thing. So the way you're going to convert is, let's say this was the original question. You define the limits based on the question. Then since you want to apply the central limit theorem, you add and subtract halves to it. So you're increasing and decreasing the ranges. You're basically increasing the range that you're approximating. And then you are subtracting, suppose this was for sum. So you're subtracting n mu from both sides. And then you're dividing all the sides by sigma root n. And then you can basically have two different CDFs that you are going to be using, right? All right. So this one's the central limit theorem. And again, it's just a simple example that was also discussed in the lecture. So let's say when you're approximating an exponential distribution to a normal distribution, you would just plug in the values of mean and variance wherever you are supposed to write mu and sigma square, right? So pretty straightforward things. Any question until here?
No, ma'am, no, ma'am. But it is exponential. How you are making it as a normal distribution?
Okay. So the central limit, so the individual random variables, so x1, x2, and xn, all of these are not exponential distributions, right? But when we are looking at the sum of all of this, that becomes a normal distribution. Okay. So x1,
Madam,
x2.
sum of exponential is not exponential. It is a normal. Is
Yes.
it a
So
normal?
when sum of a large number of independent random variables, and this is what was discussed in the lecture, that at least when you have 30 or more of random variables, and they're identical. So all of them are exponential, are x1, x2, x3, xn, all of those until at least x30. Then when you're taking a sum of all those, then you can approximate it to a normal distribution. It would almost be like a normal distribution. And working with normal distribution is simpler. There are more rules, there are more theorems. It's easier to calculate. Okay.
Okay, you are making that sum of
Hmm.
exponential variable
Hmm.
into normal
Yes.
variable as
Yes.
standard normal. Okay.
Yep. All right. Okay. Fine. So now the next thing which was started this week and will also continue in the next week's session is about statistical inference. So if you remember, we did talk about a little bit of statistical inference in the last week where we were discussing chi-square and t-test and f-test, chi-distribution and t-distribution and f-distribution, right? Not tests, but distributions. So that would be rediscussed later. But for now, um, something that was discussed briefly in one of the previous weeks was the difference between sample and population, right? So what happens is, so a population is defined as the original thing. Okay, so let's say in terms of humans, whatever inference we want to do, like whatever we want to make conclusions about, that what is the age of the average age of the population of people in India, or what are their heights, or whatever income, whatever things we are looking at, we would ideally be interested in looking at each and every person. But it is not always possible for all the things to consider everybody. So a lot of times, so you make an observation about some people. You're taking fewer numbers. So let's say the entire population is 1 billion. So you don't take 1 billion people. You might take maybe 1 million people, but also you want to be sure that whatever conclusions you are drawing from 1 million people, that's appropriate. It should not be that you're only taking, so let's say what would happen is, you might take the population of only northern India. So then whatever conclusions you're drawing might not be applicable to southern India, because region wise there can be differences. So the thing is, we are assuming that when we are taking a smaller group out of that population, that smaller group should represent the population. This is an assumption that um, we sort of always keep in mind. So that smaller group is called the sample, right? Conclusions about the behavior of a random variable of the population is drawn based on the sample. And we're assuming that the sample is a representation of the population and it would fit some sort of a distribution. We'll just call it F. It could be normal, it could be anything. We're just calling it F. So now we want to estimate the behavior of the population. So sometimes we may be interested in the mean, sometimes in the median, mode, variance. We could be interested in any sort of a population behavior. That's not important. But we would assume that the population parameter is fixed. It is a particular value. The mean of a population, if it's 10, so it's 10. It will not change to 11. It is 10, so it's a fixed value. Now, we want to estimate that population parameter. Okay. Estimate, right? So we can estimate the exact value or we can estimate the interval. So let's say when we are saying 10, are we able to estimate 10, or are we estimating that it's between 9 and 11? All right. So it could be either of the two things. And what is the difference between parametric and non-parametric setup is something we will discuss a little later. But basically, when we know what kind of a distribution we are looking at, when we know the mean, when we know variance and things like that, some information is known, then we call it parametric. But when that information is not known, we'll call it non-parametric. But I understand it's an abstract concept at the moment. We'll get to it when when that's discussed. Okay. So basically, from this slide, what I want to tell you is that there is a population. So the population is the reality, and there is a sample, and it's the sample through which we want to estimate information about the population. We want to estimate some information about the population, right? So now what we do is we want to estimate, let's say we want to estimate theta. Okay. And we'll say that a statistic Tx is an estimator of theta. So theta prime, so the original value is theta. The actual value that we wanted to derive is theta. But using Tx, using a statistic, we were able to estimate it to theta prime, theta hat. This is how it's denoted. Right? So now, how good is theta hat? How good is theta hat as compared to theta? This is something we want to find out. So there are a lot of checks that one can do to estimate the goodness of this estimation. So we would be discussing two of these. We have discussed two of these in this week, and I'll just brief you through it. So the first one is that about the biasness, and the second is about the efficiency. So let's see what that means. So this one's a very simple concept, right? So you had an original value theta. You estimated it to be theta hat. If they are different, then you would say it's unbiased, it's biased. So bias means differences, or it's not correct, something like that. So you would want it to be a correct estimation. So if both of them are the same, then there is no difference. So there's no bias. So then you'll say that the estimator is an unbiased estimator. But if it's not, then you can calculate the bias, you can calculate the difference. And that difference is nothing but the difference between the expected value of theta hat. So now see, now the important aspect here is that theta hat is a random variable. Okay. So for random variables, you can find their expectation value, and from that you can subtract the original value that you wanted. So that's theta. So fixed value minus fixed value, that gives you the bias. Okay. So that's one thing. The second thing we want to check is the efficiency. So now the second thing we want to know is how variable is what I am estimating, right? So it's a random variable here again, right? A random variable will not have a fixed value. A random variable is a distribution, as we have been seeing throughout these lectures, right? So you want to see how big is the distribution. Does the random variable look like this, or does it look like this? So if it looks like this taller peak, then you can say, okay, you are pretty sure of what this value is like. Okay. So you can find out the variability or the variance of that estimator, and that is defined as expectation of theta hat minus expectation. Okay. I think I've done something here. I think the formula is not correct. Do any of you remember? Or maybe this is correct. I need to double check. I'm not sure. Let's see. Let's see in one of the upcoming slides. Okay. Anyway, so what the main idea is that you find the variance of that estimator. So that's one bit. So you found something about the expectation and something about the variance. And these are two things which we normally talk about a random variable, right? Now, there is also a way to combine these two properties. So you're basically adding up the variance and the bias. So you're adding up the variance and the square of the bias. So what this does is, so this is sort of telling you the error, okay, the total error. Now another, so ideally what we would want is we would want a very low bias and we would want a very low variance also. Ideal case, it should be 0, 0, but that does not happen, right? So there would be a finite value of the variance of theta hat, and there would also be, just give me a second. Okay, sorry. Yeah, so the thing is that both variance and bias square, they're both going to have some finite values. So MSE, which is the mean squared error, that would also be a fixed value. Ideally, we would want MSE to be 0, but it's not. It's a positive value. So what we can do is that we can try MSE to be as little as possible. Okay, so let's say you have two thetas that you're comparing, and we would do this exercise in the upcoming in a little while. So let's say you have these two thetas and you're comparing them via their variances, you're comparing them via their MSEs. So what you can do is you can compare the MSEs in terms of whether MSE for theta 1 is greater or lesser, right? So, and when you want to check greater or lesser, you can subtract or you can take a ratio, right? I mean, MSE1 minus MSE2 or MSE1 divided by MSE2, whichever one you can do to see which is greater, which is lower. Typically, you would want the lesser one, right? You would want the lesser of the two. Now, the thing is, so the way one proceeds with it is the first step you do is you check the biasness and then you check the variance. So when you're doing that, normally you would expect that, okay, so let's say you had five thetas to begin with, theta 1, 2, 3, 4, 5. Let's say 1, 2, and 3, they had a very low bias, and 4, 5 had a slightly higher bias. So you would normally say, okay, I will not consider 4 and 5, right? 1, 2, 3 have a low bias, so 1, 2, 3 should be good. But maybe 4 and 5 have a very, very low variance, whereas 1, 2, 3 have a very high variance. So what happens is you need, it is like a trade-off. So if you're choosing something with a no bias, but if the variance is very high, you ultimately end up increasing the MSE, right? So for example, what I mean to say here is, let me just show you an example. So our aim is to reduce MSE, right? So we want low MSE. Now let's say in case of theta 1 and theta 2, the bias and the variance, let's say the bias is whatever 2, the variance and the bias is 3. But the variance here is say 1 and here it's 10. Okay. So now, sorry, this is, let's say it's like this. Okay, so this is 1. So now what is going to happen is if you just took a look at the bias, you would say, okay, theta 1 is nice. So let's go with theta 1. We'll ignore theta 2. But the idea is that you need to consider both of these aspects. All right. So if you consider both of them, you realize that this is better. All right. Okay. Cool. So So this is what it says here, that at times an estimator with a relatively higher bias may be chosen if the variance is much, much less. So oftentimes, this thing called the uniformly minimum variance bias estimator, that means or everything is low for that estimator is not necessary. Okay, maybe it does not have the lowest variance, maybe it is not unbiased. So the U here stands for unbiased. So what we are taking here, like let's say the bias here was 0. So it's really nice. But what happens is here, although it's biased, but the MSE is still the lowest. So you end up choosing theta 2. All right. So this is about the efficiency of estimators. One final thing which is also checked is that when you're taking this variance of theta prime, another additional calculation that one can do is calculate the corresponding standard error, right? So it's variance of theta hat. You estimate that, right, for the sample. So variance of x bar, this is indicating the variance of the population, and that x bar here is the mean, right? X bar we always used to denote as mean, and we have seen the mean of a population. So the thing is that the variance of x is sigma square. So the variance of x bar is going to be sigma square by n. And you can take the root of that. This works for the population, and the sort of when you're estimating the value for the sample, you put a hat, and so these are the values for the sample, right? So don't get confused in the notations. Standard error is basically the square root, the positive square root of any value. So here in this case, it's the variance. Okay. All right. So we will take one example that was also talked about in the class. So again, mentioning when we are, so what we are doing is we have a normal distribution. The mean is mu, and in this case, let the variance be 1. We don't know what mu is, but we know that the mean is mu. That's all. The mean of the population. But now we want to estimate it from a sample. So we are defining 4 samples here. Okay. The first sample is the mean. The second sample is the average of the first 2 observations. The third sample is just a single observation. And the last sample is for a constant. For any constant A, you are multiplying A with the corresponding values of the random variable, and you're summing them up. All right. So for that, so you have these 4 estimators. And so what you're going to do for these samples is you're going to find the expectation. So the expectation for the first one, the expectation of a mean. So you plug in these values and you get mu. For the second one also, you get mu. For the third one also, you get mu. And for the fourth one, you get 1. For the fourth one also, you get mu. Given that there is a certain condition about the summing up of these constants. Okay, so in all cases, you get mu. For all 4 types of samples that you have taken from the population, which is normally distributed, you get a good estimate of mu, right? So they are all unbiased, so as to say, right? You expected mu and you got mu. So that's good. But now you want to check the variance also. So here we are just taking the first 3 cases. So unbiasedness we saw in the last slide. The variance in this case, so if you remember how to calculate the variance, so this is mean. So the mean would have 1 by n, right? Because the variance, original one was 1. And here you're dividing them by n. So you also divide this by n. Right? The variance, when you're taking 2 random variables, when you're summing them up, you divide. So it's n plus n. So that's going to be, you add up the variances and you divide it by the square. So that's going to be half. Right? And for the last one, it's just a single observation. So the variance stays what it was. So it's 1. Now, the first case, now through the variance, you can see that out of the 3 cases, the first case has the least variance. Right? So then that would mean that the first one has the lowest variability. So the efficiency of that estimator is really good. So out of the 3 cases, you would end up choosing the first one. Right? Does this make sense? Hello? Any questions? Okay. If not,
Can you unbiased?
say that again.
Yeah, that one.
Hello?
Unbiased. The estimator is unbiased if this condition is satisfied, ma'am. Expectation of mu1 cap equal to mu.
Yes, estimating, when you take the expectation, so expectation of any of these things.
Random sample. Okay. This mu is a population mean. X bar
Yes.
is a sample mean.
Yes.
Okay. Why you are defining that average of x1 plus x2 as mu2 cap? What is
So
the purpose?
this is just 4 different cases. We are just saying, so you are taking a sample, right? So ideally a sample should be representative of the population. That is what we saw a couple of slides back, right? So these are just 4 ways in which we are defining the sample. They're just for demonstration purpose. Obviously, the first one is the best estimator. You can already
XBAR is
see.
sum of average of n random sample.
Yep.
Okay, that why you are taking only 2 samples,
So
2 random.
exactly, this is just for demonstration. This is just
For
a
what?
it is just for example. If this
Example.
was how, if this is how a population was, if this is how a sample was defined, then what would
Okay.
happen? So in that case also, you could estimate the mean quite well.
Oh,
Even 2 observations were enough to get the mean. So the mean was still good, but the variance was not really great.
okay.
The variance was great when you took all the samples, all the
If you find it,
observations.
then only we will call it as unbiased estimator.
Yes. So it is unbiased in all case, right? So when we want to estimate the mean, we could take 3 types of samples in this
Yeah.
example. So in all of those
Yeah.
cases, the expectation value was still mu, which is good. But the variance, so for example, it's like this. So this is mu. In one case, this is the distribution. In one case, this was the distribution. In one case, maybe this was the distribution. Okay. So in all cases, you got mu as the mean, right? They're all centered around mu. But the variance, so see, this one has a variance 1. Let's say this one has a variance half. And let's say this one has a variance 1 by n. So the lower the variance, the better. You are very sure that you are estimating mu correctly. So this graph is most probably this one. And this graph is this one. And this graph is this last one here.
So 1 by 2. Okay. Okay. Okay, ma'am. But the third case is only one.
Yes.
Only one.
Yeah. So exactly. So again, the question is, you have a lot of random. So it's not one observation. It is one of the random variables. Each random variable
One
has a
of the
lot of
sample it has
observations.
more observations. It is one of the
Yes.
sample.
Yes.
Oh, okay.
All right.
Okay. Yeah.
So again, it is the same thing. What you're saying is, why are we taking only one, or why are we only taking 2? So that is what the
Yeah.
idea is. Always taking more is better. So which is proved by this example, right?
Okay.
Right? Okay.
Why we denoting the mu 1 cap? We can keep x bar itself or x1 plus x2 by 2 itself. Why we keep one more notation? What is the purpose of that?
Hat. Say that
Uh,
again.
Madam, we are taking mu 1 cap, mu 2 cap, mu 3 cap.
Mm-hmm.
We simply keep as it is, no x bar or x1 plus x2 by 2 or x1. What is the
This is,
purpose?
so hat means when you're estimating something. When you're talking about a sample. So basically, when you're talking about a sample, how
Yeah.
you're defining the sample, then you use this hat symbol.
Sample, it's a part of the population taken from the when process of sampling.
Yes.
Okay.
So the thing is that you had a lot of options. You had the option of taking the average of all the random variables, which is case 1 here. You had the observation of taking only the first 2 and doing an average of those. You had an option of taking only the first one. So there are 3 ways. So in each of the 3 ways, you could estimate the corresponding value of the mean. So from the 3 different types of samples, you estimated the population mean. The first estimate was mu1 hat. The second estimate was mu2 hat. The third estimate was mu3 hat. So we are talking about the estimate here. Estimate based on a sample. That's why you're talking about this hat here.
Okay. Okay.
Okay. All right. The last topic that was discussed this week, it is a little complicated even for me. So I will try to explain it to you to the best of my ability. In case it is not clear, let me know. I will prepare it better and explain you in the next, either of the next 2 classes. But so let's see how this works. So we just talked about two things, right? We are estimating the value itself, and we are seeing what is the variance. So for the second case, for the variance case, um, we we are doing this calculation, right? So now we don't know how low of a value is enough. So it's possible that maybe 0.1 is good, maybe 0.2 is good, we don't know. So what can be done instead is we can estimate what is the ideal low value for a particular distribution. How low can it actually be? How low can the variance actually be? So anything greater than that, so anything slightly greater than that would be okay. For example, if you have an estimate 0.5 and 0.7, normally you would say that okay, 0.5 is good. But maybe um so right, so maybe 0.51 is also equally good, or maybe 0.7 is also good, because the lowest it can go is only 0.5. So okay, so let's see some more examples through it. These are some assumptions that are not entirely applicable. Like, we don't need this just immediately. I'll get to it a little later. So these are the screenshots from the lecture slides themselves. So the idea is that, let's say you got two estimators, 0.5 and 0.7. Normally you would say that 0.5 is good, but maybe the lowest value that it can go is actually 0.1. So in that case, even 0.5 is not that good of an estimator. The estimator with variance 0.5 is not that good of an estimator, right? Does this sentence make sense? So what we are doing is we want to estimate what is the minimum variance that an unbiased estimator can have. So again, an unbiased is given as this X bar, a bar below, okay? A lower bar in this case. So what we are doing here is we are taking the first differential of theta, the actual estimator. We are squaring that up. And the denominator is we are multiplying n, and we are finding the expectation of single differential of log of the PDF itself and squaring that up. Now this would seem very, very complicated. So let me go to one of the examples, and then if it's still not clear, then we will rediscuss this. So basically, what the Kramer-Rao inequality, or the Kramer-Rao lower bound, which is we've said to be as CRLB, what it does is it will tell you what is the accuracy that you can observe. Maximum accuracy or minimum variance. So the minimum variance, that is, let's say it's 0.1, 0.2, whatever that is given by either of these formulas. So you can see that the numerator is the same in both cases. It's just the denominator, whether it's the first differential or if it's the second differential here, right? So d by d theta, like del by del theta, or if it's del square by del theta square. Are you familiar with the concept of single differential and double differentials?
Ma'am, what do you ask, ma'am?
Are you familiar with the concept of single differentials and double differentials?
Yes, ma'am.
Okay, fine. So again, so these two formulas, they are the same. They like either of them can be used, like a single differential or the double differential, this one and this one. So now the denominator in this case, so expectation of this value or expectation of the other value, they are both called the Fisher inequality. Fisher information. Okay, so we will just get to it. We will see how what's the use of this thing. But okay, so before we do any examples also, so sort of one example that was discussed in the class is for a normal distribution, so for a normal distribution, the CRLB of mu and of sigma square is these values. And this would just come in handy for some of your questions in this week's assignment. Okay. The derivation is not, it's a little lengthy because a lot of calculations are involved. So I will not get to it, and I will also not recommend you to go through it unless you're interested, of course. But I would instead recommend you that you can remember this, and you can directly use these values. So CRLB of mu and CRLB for sigma square is these values respectively. Okay. Now, so this is what was discussed this week. We will just see a few practice questions now. All right. Do you want me to discuss anything else before we go down to the practice questions for this week? Hi Abhishek. It would not be possible for me to give a quick recap because it's been about half an hour since we've been discussing. The session is being recorded anyway, so maybe you can take a look at the recording. I now have about 9 questions that would give you an idea of what all was discussed this week, and these are questions which are similar to your assignment, very similar. So I hope this would anyway be helpful for solving the assignments. All right. So let's see. All right. So the first question here is that suppose there are 2 fair dice which are tossed 1200 times, and let X denote the number of times a total of 8 was occurring. Now, we have seen previously that this sort of a distribution would be a binomial distribution, and the parameters would be, so n in this case is 1200, p is, let's say it's 1 by 6. So now you want to find the normal approximation to getting this value. Okay. Now, it might seem abstract at first, but if you remember, this is going to follow. So the keywords in this thing is binomial distribution and normal approximation, right? So a binomial distribution is being approximated to a normal distribution. So we are going to use the central limit theorem for this, right? And we had seen that when n is a very large number, then you can do this. So in this case, n is actually 1200. So we can do that, right? So the way we are going to start with this is, so we want this value. And now in this case, so if you remember from CLT, there were 2 ways we can apply CLT. We can do it for the sum and we can do it for the average. Now, when nothing is specified, so now think about it. When you have a lot of random variables, if you take an average of those, you would still be in the range of those random variables. When you take a sum, it's going to be much higher than those random variables, right? So if your random variables are between 1 and 10, you take the average, you still stay between 1 and 10. But if you take sum, you're going to increase it to 20, 30, 40, right? So for such a question, for the question that's given here, you would be using the thing for average. All right. So the way we are going to go for this, okay, sorry. So let me just show the formula that we're going to use this one, right? So you're going to take the average, you're subtracting mu, and you're dividing by sigma by root n. So what we are going to do here is that we are going to subtract mu. All right. So mu in this case, for a binomial distribution, you remember mu is this value, NP, right? Can anybody confirm? right? Do you remember we talked about this very initially, I think the first couple of weeks or so, right? So mu of a binomial distribution is NP. Do you also remember what's the variance of a binomial distribution?
NPQ.
NPQ. Perfect.
NPQ.
Perfect. Great. Right? So that one is so when P is 1/6, Q is equal to 5/6, right? Right? So this value, if you multiply, I think it should come to 500/3. Okay. So when you do that, so 90 minus 200 divided by, let's say, so this is going to be uh, sigma by root n, right? Or root n by sigma. Sigma by root n. Okay. So it's going to be 500 by 3 into root of 1200. This is less than x minus, again, the same thing. And here also you're going to have the same thing. Okay. Now, now the way you are going to solve this is, so this actually becomes a z. It becomes a random normal variable, right? So you'll have some value here. Let's say this is a and let's say this is b. So now the way this you can write it is x less than z less than b minus z less than a. So you can find out the value of so basically you're finding two different CDF and you're subtracting those. It's just that the values here are a little bit complicated. I mean, root of 1200, you subtract and all of those. So you might have a little complicated values, decimal values, but whatever it is, you can easily calculate that. And the first question or the first, some of the one, like question number 1 or 2 in your assignment is of the same lines. So I'm not solving it entirely, but this is how you're going to do it. All right. The next question is also very similar. So I would like you to tell me what values I fit where. Okay. So consider the amount of coffee dispensed by a coffee machine. Consider it's a random variable and it dispenses 100 ml coffee with 16 ml of standard deviation. Find the probability that the average coffee dispensed in a sample size of 64 is at least 105 mLs. So tell me, how do I go about it? It's the exact same question as before. So what values do I plug in where? Can any of you unmute yourselves and walk through this with me? So the first step you need to do is you define the probability. What are we interested in? What limits are we going to write here? X less than, X greater than what? If any question is not clear, then please let me know. This is what the problem session is for. Nothing? Yeah.
Probability of x bar
Hmm.
greater than or equal to 105.
Perfect. Very good. Okay. So X bar is something you've said, and that's right. So now what we can do is, since we would like to convert this into a continuous random variable, we would just subtract mu. So what's mu here?
Hundred.
Correct. What is sigma? What is sigma square? Any of these values?
Sigma square is 16 square. Sigma is 16.
Good, good, good. And n is?
N is
Right?
64.
Yeah. Okay. So what we are going to do is again subtract mu and divide by sigma by root n. So it's going to be 105 minus 100 divided by 16 by root n. That's 8. So probability of this z is greater than 5 by 2. So that's equal to z greater than equal to 2.5. So now this is a standard normal distribution, right? Normal 0, 1. So in questions, if you are going to be asked, in the assignment, if you're going to be asked questions, then you would just need to find out, you would be given the value or you'd be given a table through which you can calculate this. But just for demonstration, if you remember in one of the initial lectures, we had seen this thing, normal distribution calculator, right? This one. So now we have a standard normal. So this is 0, 1. And we are interested in value greater than 2.5. Right? So I'll just write 2. What happened? Yeah. So I'll just write 2.5 here. We are interested in this. So it's going to give me 0.0062. So this thing. Right? So that's it. So that's the answer. Okay, 0.0062. Fine. So this is how you can solve questions from the central limit theorem. Now this one is, it's also the exact same question. So again, you can find out what is going to be, sorry. So you can go and find out what are the values. So N in this case, insurance company has 10,000 policyholders. It's a random variable with mean 180, right? And standard deviation. So just be careful not to mix standard deviation and variance. That's a very common error and a very easy error to make. So N is going to be 10,000. So the probability that the total yearly claim exceeds 4.8. So this is the important bit. Here it's saying total. So now you would not be calculating average like we did. Here we did average. In the previous one, we did average. But now in this case, we are going to do it for the total thing. Right? So now we are going to use this part. Minus n mu divided by sigma root n. Okay. Anyway, so we want to see that it exceeds 4.8 million, and million means 10 to the power 6. So here you want to n mu upon sigma root n. So it's going to be 4.8 into 10 to the power 6 minus, this is going to be 10 to the power 4 into 180 divided by sigma is 16,000, root n is 100. Okay, so you calculate it, and whatever the value is, that's going to be your answer. Okay. Does this make sense? Okay. The next question where we went on to talk about estimators is, so T, that's the statistic, it's calculated from sample values x1, x2, and xn. We want to estimate some sample parameter theta. Now, I was a little late, so I did not have time to write down. So I've just taken a screenshot of where I have the question from. So the answer is already here. But the main logic behind this is all of these could be estimators. They could all be statistics. But the thing is, so when you want to estimate mu would not be a formula. Mu would not be in that statistic itself. Okay. So if you want to estimate something, that should not be in the formula itself. So which is why the other option, which does not have that estimator, is the answer. Okay. So that's one question. Okay, there are a few questions now about unbiased estimators and variance of these estimators. So if you have a random sample, and this is the probability density function, which of the following statements is true when you're defining sample mean as x bar? So this is how x bar is. So is x bar, which is the sample mean, is it an unbiased estimator of the population mean? So is it unbiased? Is it biased? Or is there not enough information? Or in general, you cannot estimate the bias of a sample mean? Which of the four do you think is correct? And can you tell me why? So the one thing that is important here is that when you're talking about estimators of something, a lot of times the original distribution does not matter. It is the way you are defining something matters, right? So if you remember this question that we were talking about here, this is how you're defining it. It does not matter whether the original distribution followed the normal distribution, whether it was exponential, whether it was Poisson's, whatever it was, that does not matter. How you're defining that estimator is what matters, right? So in questions like these, main focus should be here. So, and this we know, we've seen previously that this is actually a good estimator. We just saw the slide that I showed you. The first example was this one. So it is an unbiased estimator. And we know that sample mean does give you population mean. Likewise, here you want to calculate, you want to,
Ma'am, 50 question show, madam. I want to take screenshot.
okay. Anyway, I will be uploading the slides right after this class on the Google Drive. And this recording will also be uploaded to YouTube. Okay. Done?
Okay, madam.
Yeah. Okay. So the same thing can be that if you want to estimate the sample variance. So, I mean, if you want to estimate the population variance, then if this is how you're defining and that estimator, then that would also be a unbiased estimator, right? So these things are what we have seen previously. The more important bits come now. So, okay. So let x1, this be a random sample from a population. They could have any probability distribution. The only thing is that the mean and variance are given to you. And this is how you're defining the sample variance, right? So here, okay, sorry. This is going to be n here. Right. Okay. So the thing is, now if you remember, the way sample, sorry, yeah. So the difference in these two questions is here you have the sample variance that is n minus 1, right? But when instead you define it with n, there is a bias. And the bias is this ratio of 1 upon this n into n divided by n minus 1, right? So that's going to be the bias here. So it is a biased estimator and the bias is n upon n minus 1. Okay. I think this is the last or the second last question. Okay. Okay. This I let me just show this to you. Okay. So what we've been doing with, so there are four things in this question. We're talking about the means, we're talking about the variance, and we're estimating both of those. Oh, sorry. Okay. The variance, we're not estimating the variance here. We are just, the estimators of mu are only there, but we want to compare the bias and variance of these estimators themselves. So, all right. So let's see this one by one. First of all, we want to compare bias of mu1 hat, right? So we had seen that it's going to be the expectation of mu1 hat minus mu, right? So that is going to be, so the expectation here, so the way we are going to write this is expectation of x1 plus x2 by 2 minus mu. So this x1 plus x2 by 2 is actually going to be mu minus mu. So that's 0. So there's no bias here. Instead, when you want to calculate the bias of mu2 hat, again, formula is the same. So this one would also have mu minus mu, right? Mu plus 3 mu, that's 4 mu. 4 mu divided by 4 mu is mu. Mu minus mu is, that's also 0. So we've compared the bias net and both the estimators are unbiased. Now, when you want to calculate the variance, so variance of mu1 hat, so now the variance here is going to be sigma square by 4, right? Because here it's 2. Do you remember this thing? Variance of ax is equal to a square variance of x, right? So this is what we're using. In this case, a is 2. So this becomes 4. Sorry, this is 2. Yeah, we are adding the variances to 2 sigma square divided by 4. So that's equal to sigma square by 2. And then variance of mu2 hat, that's equal to, so this is going to be 4 of sigma square divided by 16. It's going to be 1 by 4. Sorry, just let me double check. I think I've made a mistake somewhere. It's going to be 1 by 2. It's 1 by 4 plus 1 by 4. So 2 by 4. And this is 1 by 4, so 1 by 16 plus, so this is going to be 10 by 4 actually. So 1 plus 9. Here it's 1, here it's 3 square. So it's going to be this thing. That's going to be 5 by 8 sigma square. Okay. So you can see here that the variance here it's greater, right? This one has a higher greater. So this is not as efficient. This one is a better estimator. Okay. The first one is a, so you're going to say that variance of mu1 hat is less than variance of mu2 hat. All right. Okay. Okay, yeah. So we have this one final question here. This is from the lower bound of the Kramer-Rao inequality. So we had seen something called the Fisher information, right? And if you remember, the Fisher information has these two forms. The first differential and second differential. So I would like, if any of you are more familiar with log and differentials, then please let me know if I'm calculating this correctly. All right. So what we want to do here is want to take log of, so we are interested in the denominator here, right? So log of fx for a given theta, we are going to take the first differential or the second differential of that. Okay. So we have theta x theta minus 1. We are going to take a, let's do a single differential of this whole thing. Okay. So when you take, when you do a natural log or log of two different things, it's a product. So what you can do is, you can write it as ln of theta plus ln of x theta minus 1. Right? Please let me know if I'm making a mistake somewhere. So it's going to be this of ln theta plus, okay. Now the thing is, log of this thing, okay, we can't change anything here. So it's going to be d by d theta ln of x theta minus 1. This thing right here. Now this becomes 1 by theta. And this would be some value in terms of x. Right? Okay, let me just check. I think this is going to be ln of x. This thing, like it's a known thing that log of a constant to the power what we are differentiating it against is going to be ln x. Now, what is going to happen is, now the first differential here is in terms of theta as well as x. But we don't want x in the Fisher information. So what we can do is, we can do a double differential of the whole thing. So it's going to be this again of 1 by theta plus ln of x. Now ln of x is a constant, right? So what we get now is just del by del theta of 1 by theta, which is going to be minus 1 by theta square. So that becomes your Fisher information. So both of those are correct, right? But we are mainly going to, so it depends on which one you, so which one gives you a better estimate. So since we don't want it in terms of x, we will just do away with dx and we can take a second derivation. All right. Okay. Oh, all right. So these were the questions that I wanted to discuss this week. Do you have any questions from the last week's assignment that you want me to discuss? Anything from here?
No, ma'am. I just want to say thank you to you. Because of you, I got 100 marks in previous session.
Oh, that's great. Thank you so much. It's
And
nice to know that.
I'm
Sorry.
regretting I didn't watch your session previously.
Oh, that's okay. It's perfectly okay. I am also sort of learning. So I think today's session was not, like, I did make a few mistakes. It's not, I did not have a lot of time to prepare for this. But yeah, but it's a great learning experience, I think, for all of us. So it's great. And thank you for
Yes,
telling
ma'am.
me.
Yes.
Yeah. Okay.
As per schedule, today there were two sessions, so I
Yeah, right.
mistakenly joined the wrong session. So I thought you weren't there, and
Okay.
I
Yeah,
joined
yeah.
later.
No, that's okay. So anyway, the session is recorded. In case you would still like to go through
Yes,
it,
ma'am. Yes, ma'am. I
it will,
know.
I'll upload this. So yes, I could not take a session last Friday. I had some work. So the deadline for this week's assignment is tomorrow. So don't
Yes,
forget
ma'am.
that. And we'll have the next session as per the regular schedule. So that's going to be on Friday in 3 days. And I'll see you all again then. Okay.
Thank you, ma'am.
All right. Thank you so much, everybody, for joining.
Thank you, ma'am.
Okay, good night.